Recognition by Ala Salehi.
Good afternoon, everyone. My name is Ala Salehi, and thanks for joining me today. I'm going to walk you through my master's research presentation on pressure-based gait recognition feature extraction technique for footwear agnostic identity recognition. This work represents a step forward in understanding and enhancing identity recognition system through gait analysis, focusing on challenges posed by various footwear. When it comes to biometry, regardless of the modality or application, two essential tasks are identification and verification. Identification involves assigning label to an individual, essentially determining who is the person. Verification, on the other hand, confirms whether the individual matches the claimed identity. For instance, as you can see in the left side, the photo app uses the face identification system to tag the users in a photo. However, the iPhone Face ID system employs face verification to capture a live photo and check whether it matches the stored user and to enable the secure access to the device. In this research, these two distinct tasks, identification and verification, collectively referred as identity recognition. Biometric provides a means to recognize individuals by leveraging physiological or behavioral characteristics. Common examples include for physiological face recognition or fingerprint scanning, and for behavioral modalities, voice recognition or signature analysis. Although biometric systems are widely used, they face some limitations. For example, face recognition can struggle to the occlusion caused by accessories like hat, glasses, or face masks, and voice recognition is prone to error from background noise or accent, making it less reliable in uncontrolled environments. This is where gait recognition can be an alternative approach that doesn't suffer those challenges. Gait recognition combines both physiological or behavioral characteristics, addressing the limitation of existing methods. It studies how individuals move their bodies during walking, capturing their unique walking pattern. However, verbal sensor installation and calibration is a tedious task. Additionally, video-based approaches affected by environmental conditions and can exhibit racial and gender biases. Moreover, privacy concerns arise within video-based methods. In our study, we focus on pressure-based gait recognition, aiming to overcome those challenges. Here you can see a sample of foot pressure captured from step scan trial. It's worth mentioning that this research is part of a larger project in collaboration with the industry. For building an effective gait recognition system, we need to understand the application scenarios. There are two key scenarios: home and medical application, where we have limited number of subjects with fewer users and often barefoot. We also have public scenarios such as offices or airports with many users and with diverse footwear. Most research focuses on barefoot or a footwear control scenario. However, in public application, it's unrealistic to collect all possible footwear for the training and test. Therefore, identifying user wearing unseen footwear becomes a significant challenge. Our work tackled this by addressing diverse footwear scenarios and focusing on this problem. Let's see how footwear can impact the recognition of gait patterns. Footwear affect gait in two ways: physical changes that each footwear can alter the effect of sensing, which impact the shape and texture captured from pressure data, and behavioral changes at different shoe impact of how people can walk. For example, wearing high heels or flip-flops, it can significantly alter the gait pattern. The combination of both physical and behavioral factors play into difficulties in recognizing gait. In analyzing gait, we can break the problem into two approaches: closed set, where the system trained to know footwear to adapt all the variability of footwear, and open set, where the system faces unseen footwear, making the generalization more challenging. These two main challenges therefore align with two main aims of this research. First, optimize closed-set performance by improving model resilience to all the footwear. And second, address the open-set challenges by generalizing to unseen footwear. We aim to maximize performance in the closed-set and assess feasibility of open-set problem. This motivates us to explore resilient feature extraction methods. Earlier gait study used center of pressure COP or ground reaction force GRF, which lacked the special detail. StepScan technology now enables high-resolution data, allowing us to treat gait as both a special and temporal features. We explored two feature domains in this research: a special domain for detailed pressure pattern and a special temporal domain to capture dynamics of gait pattern. Let's now dive into dataset and methodology for this research. For this work, we primarily use CASIA-D dataset. Additionally, we tested the generalization of our method on dataset with more varied samples. We used pilot subset of UNB dataset, which is part of an ongoing data collection process at UNB. Although CASIA-D has 97 subjects, it only has 14 subjects with different footwear classes. Therefore, to make a fair comparison, we use 14 subjects from UNB dataset. On the right side, you can see the setup we have in the UNB, including 12 pressure-sensitive tile and 7 video cameras. The bottom video shows an example of foot pressure data captured by StepScan tile, which we analyze to extract walking patterns.
They crash? You can't, can you exit out of the presentation? Yeah. Oh, it actually crashed, yeah.
Oh, fine. We have 2 hours.
May.
Probably we'll be done in around an hour, so.
The pressure data consists of 3D pixel time series. In processing the state, we segmented this data into individual footsteps, standardizing it for analysis across the entire CASIA dataset. The pre-processing step included alignment, that all the signals were aligned based on same angle, and then zero pressure region were cropped to fit the bounding box. For the interpolation step, data was resized into the uniform size regardless of the different foot size. For normalization, the contrast was normalized for consistency. And finally, all the right foot data flew to the left side, ensuring uniformity across samples and effectively increasing the amount of data available for each subject. With the data prepared and segmented, it was used to train the models. A common pre-processing framework was applied across all models to ensure consistency and comparability through the research. Now let's discuss evaluation framework. For the closest scenario, samples from all 3 footwear classes, barefoot and 2 types of shoe, were randomly spread across train and tested. This allows model to see examples of all classes during train access. For the open set scenario, data for 1 type of shoe was held out as unseen test set, while the remaining 2 footwear classes were used for training. This evaluates the model's ability to generalize unseen footwear. For the performance evaluation, we use key metrics. False acceptance rate measures how often unauthorized user falsely accepted, and false rejection rate measures how often genuine users are rejected. A major challenge in biometric is class imbalance, where certain classes have more samples than others. This is an inherent in verification problem because it's one versus race classification task. These metrics were chosen to account for such imbalances. This diagram outlines the overall pipeline of this research, including dataset and preparation and data splitting, feature extraction, evaluation for both identification and verification tasks. The main contribution of this work lies into the feature extraction block, where we initially explore a variety of techniques for dimensionality reduction. While existing method offered some benefit, they struggle to generalize an open set scenario. For this presentation, I'll focus on our novel contribution in feature extraction and their role addressing footwear variability challenges. The first novel algorithm I proposed was UMagnet, a special feature learning architecture that addressed limitations in previous approach. As explored in chapter 4 of the thesis, we evaluated feature learning networks such as PCANet or PCNet+, which showed promise but constrained based on their linear projection technique. Motivated to overcome these limitations, we introduced UMagnet, a method leveraging nonlinearity technique of UMagnet to enhance feature extraction performance. Let's begin with the special information extracted from pressure data. For a special feature extraction technique, we converted 3D pixel time series to 2D features such as the well-known P100. P100 represents peak pressure image, capturing the maximum pixel value throughout for each point throughout the whole time series. On the right side, you can see samples of P100 image for different footwear classes. As can be seen, the visual characteristics vary significantly based on the footwear type. While previous research demonstrated the promise of P100 feature, it primarily focused on barefoot data. In this work, we investigate how different footwear impact the model's performance. UMagnet followed the structure and architecture similar to common CNN convolutional neural networks. A key difference is instead of learned kernels through CNN training stage, it uses the UMAP-based kernel. This approach reduces the need for large data sets since UMAP-based kernel doesn't require the extensive training phase. This architecture allows us to effectively learn special features from limited data, making it resource-efficient alternative to the traditional CNN. Here you can see UMagnet provide improvement in a special feature learning compared to the baseline P100 significantly in closed set. Although UMagnet provided modest improvement in a special feature learning, its performance in open set problem was still limited. One potential issue that special feature learning networks are heavily inspired by image-based approaches, which only process special information. Earlier results in this research indicated that combining spatial and temporal information yield better generalization. So, while special methods like UMagnet improve upon handcrafted approaches, their reliance solely on spatial data limited their robustness, especially in the open set scenario, as you can see in the right-hand side. This realization led us to explore special temporal approaches to improve performance further. Building on the previous insights motivated us to incorporate temporal information, exploring spatial temporal models that leverages both spatial and temporal data to improve performance. We began with GatePart, the state-of-the-art method from vision-based gait recognition. For the first time, we applied these vision-based approaches to pressure-based gait recognition. The key concept underlying GatePart is it divides image into regions to capture region-specific information with the goal of improving its resiliency to different clothing conditions. In the original pipeline, gait energy images or GI were applied as an input of the model, process different horizontal regions of the GI to learn representation of aggregate temporal features. In this work, instead of GI, we use pixel time series to explore this approach if it's applicable in the partitioning for the pressure signals. We propose a novel architecture called Footpart, specifically designed to enhance the utilization of 3D pixel time series data and segment the foot into 4 key parts: hindfoot, midfoot, forefoot, and toes. These regions were selected based on the biomechanical researcher. Using dynamic time warping DTW, we calculated the relationship between these regions for each footstep. The fused data from pixel time series and DTW passed through parallel line short-term memory, LSTM, enabling the footpart to better capture spatial temporal dynamics. Now let's compare the performance of footwear with the baseline of Cassidy dataset. This slide shows the performance of different spatial temporal models compared to the baseline. In closed-set scenario, footpart achieved the highest accuracy over 98%, significantly outperformed other models. In the open-set scenario, on the right-hand side, you can see footpart also led with the accuracy over 73%. This progression reflects the strength of each approach. LSTM captured temporal features, but lack of any spatial information. Gait-part improved the spatial and temporal learning using region-based techniques. And footpart take it further by combining regional analysis with DTW, resulting in the superior performance. These results emphasize the importance of integrating spatial temporal features, particularly in open-set scenarios, where the generalization is crucial. As I mentioned earlier in the presentation, although these models developed on the Cassidy, the availability of UMB dataset led us to evaluate the generalization to a completely unseen dataset, resulting indicate that the model generalized well. Here, we compare model generalization across Cassidy and the new UMB dataset. In the closest scenario, footpart achieved high balance accuracy on both datasets, with over 96% accuracy closely matches performance with the UMB. In the open set scenario, footpart maintained its lead, achieving 72% on UMB, just slightly below Cassidy. These results confirm footpart adaptability and robustness across datasets, despite differences in sensors and participants. Importantly, the trends are consistent, further validating its generalization capabilities. Here, a consistent performance is seen when we generalize model to the more complex task identification. Footpart leads in closed set identification on the left-hand side plot, achieving over 96% on Cassidy, the dark blue bar, and 95% on UMB, the dark orange one. Importantly, its robustness extended to a more challenging identification task, where it maintained its lead despite the increase of the complexity. In the open set scenario on the right-hand side, it outperformed other methods with accuracy over 50% on Cassidy and 52% on UMB. For the significant advancement achieved in this research across both dataset and task, footpart consistently demonstrated its superiority. For verification, it achieved notable accuracy in both closed set and open set scenarios, with minimal performance loss when transitioning from Cassidy to a novel UMB dataset. Importantly, its robustness extended to a more challenging identification task, where it maintained its lead despite the increased complexity. These results highlight effectiveness of spatial temporal modeling, particularly footpart's ability to integrate local spatial features with dynamic temporal relationships, even under challenging conditions like unseen footwork. The finding underlines the importance of designing systems that can realize across datasets and unseen conditions. While this research achieved significant advancement, there are few limitations pointing to a promising future direction. First, we analyze single footstep data, but studying multiple footsteps could reveal richer gait patterns and improve the performance. Additionally, as mentioned earlier, feature learning networks reliance solely on spatial data limited their robustness. Therefore, upgrading feature learning network to better utilize spatial temporal data or converting 3D spatial temporal input into 2D formats could further enhance their capability. Moreover, leveraging hybrid approaches, for example, combining pressure-based methods with vision or wearable sensor could address broader challenges. Overall, deploying these models in practical scenarios like security or healthcare remains a key goal. This direction aims to build a strong foundation of this work, moving toward a scalable and real-world gait recognition solution. Finally, it's worth mentioning that this research is funded by industry and the NSERC Alliance, and was part of a larger project in our incredible research team. Thank you for your attention.